All right, so today we are going to talk about buffers again today, but we're going to apply that to a titration calculation from start to finish. We need more room, so I'm going to add a page and then probably add another page after that. So we'll start with one page and then I'll add it as I need to. All right. So we talked about the definition of a buffer the other day, and so you guys should understand now that a buffer is a solution that is designed to resist pH change. All right, more specifically, reduce the impact of adding an acid or a base. So let's talk about a typical pH curve and what is going on at each point, because there's different things going on, and it's really important to understand what's going on so that you attempt to solve the problem correctly. All right, so let's say I've got a typical weak acid, and you have a curve that looks something like this. All right, that's pretty typical. All right, so there's some points here I want to highlight. We're going to discuss how to calculate each part of these, okay? So right here, we'll call that point A. That is the very beginning of the titration when there's no titrant added yet. All right? And then we have area B, and that is known as the buffered region. During that flat part, that is when you have a buffer. And that is why the pH changes the least during that flat part. Okay, then you have point C, which you guys should know is the equivalence point, not to be confused with the end point. Remember, the end point is only when the color change happens. All right, and then we'll have area D, which is called the excess region. Or at least I call it the excess region. And then there's one more point I'm going to insert in a different color so it stands out. This is called the half equivalence point. All right, it's the mid of the plateau, the middle of that plateau. And yes, it is in the buffered region, but it is exactly halfway between the buffered region. It's also halfway between the start and the equivalence point. So let's make a note of that. So whatever volume this is, volume at equivalence point, this would be half the volume of the equivalence point. Okay? Okay. So if we carried out a titration, and if you were asked to calculate the pH, let's talk about the different scenarios that would happen throughout this, starting with point 1, or point A. Let's see. So at point A, at 0 milliliters, let me give you a little more context here. So let's just use a fictitious acid here. Let's say that I'm using weak acid, and let's say the Ka of this weak acid is 1.8 times 10 to the minus 4, right? Just for example purposes. It doesn't matter which weak acid this is. Okay. And let's say the titrant that I'm using is 0.1 molar NaOH, which is very typical. The titrants are generally going to be your strong acids or strong bases. In this case, it's a base that we're adding, right? And we'll just keep a standard concentration of 0.1 molar. Okay. And so let's say that I have, of my weak acid, I have 10 milliliters of it, and its concentration is 0.2. Okay, so whatever this weak acid is, I start with 10 milliliters of it, and I know it's 0.2 molar. Okay? All right, so at these different points, we're going to calculate the pH. So at point A, there's no titrant added, right? So that means the only thing present is weak acid. Since there's only weak acid present, this is simply a weak acid equilibrium problem. Okay, so HB, H plus, B minus. My initial concentration, 0.2 molar. Right, just like you remember, just like what we've done many ice tables of. So let's find what the pH is. The Ka is 1.8 times 10 to the minus 4 of x squared over 0.2 less x. Let's plug in solver. Maybe you can get away with simplifying this, but I'm just going to use it because I have it. It's kind of on the fringe of whether you should ignore it or not. Okay, so for x, you should get 0.00591. And because this, remember, this is an acid, so you always have to ask yourself, what is x equal to? Is it equal to H plus or is it equal to OH minus? This is an acid, weak acid, so x is equal to H plus. So take the negative log of that value, and our starting pH is 2.228. Okay. The beginning, before you add anything, it's just weak acid. All right? Now, let's say that we have added some amounts. Okay, so let's say I've added, this is going to be like a point, someplace in point B at 5 milliliters of titrant added. Okay. So if we have 5 milliliters of the titrant, the first thing you need to do is figure out how many moles you have of both things. How many moles of sodium hydroxide and how many moles of weak acid. Okay? So 0.005 liters times, we said it was 0.1 molar. So 0.0005 moles of the hydroxide were added. We need to figure out how many moles of weak acid existed, right, that we started with. So going back to the beginning, we said that we had 10 milliliters of 0.2 molar. Okay, so 0.01 liters times 0.2 molar means 0.002 moles. Okay. There was a statement I made about whenever you add a strong acid or a strong species, and that's all strong species react to completion. That means all of the strong sodium hydroxide that I added, all of it will react. So my weak acid, HB, is going to react with OH minus and form B minus and water. Right? So let's think about what we have. We have 0.002 moles of HB. It is going to be reduced. We're going to subtract from this 0.0005 moles. Because during the reaction, during the neutralization with hydroxide, some of that HB is going to be reduced. and we will now have 0.0015 moles of HB remaining. Because neutralization occurred, we made the conjugate. We made B minus. Right? How much B minus did we make? Well, look at the mole ratio. It's a 1-to-1. Right? 1-to-1 here. So however many moles of the weak acid that was decreased by, we gained 0.0005 moles of B minus produced. Okay? So, hey, look, we have a weak acid and we have a conjugate base. So now I can calculate what the pH is by using an ice table. So I will need to recalculate what the concentrations are because with the addition of solution, the volume has been extended. So let's do this in green so it stands out. 0.0015 moles divided by a volume, our current volume now, let's see, what did we start with? We started with 10 milliliters and we added 5. So we have a volume of 15 milliliters, so 0.015 liters. Both of these divided by 0.015 liters. Okay. I don't know why I divided that. Of course, this is going to be 1/10. And then the 0.0005 divided by 0.015. Okay, so this is going to be 0.0333. Pause here and digest that for a second. Are you okay with what we've done so far? We've neutralized some of the original weak acid. We have made some conjugate base, and now we are recalculating what the concentrations are so we can use them in an ice table. Right? And we always reset the value of H plus to 0 when we work it this way. So, continuing on with how you fill out an ice table. What was our Ka? 1.8 10 to minus 4. All right. So here I get 5.3 times 10 to the minus 4 molar. So that's a pH of 3.276. And that should make sense. We did add some base. We expect a pH to rise somewhat, but not drastically. As long as there are both parts of the buffer present, your pH will not change too much. Okay, so 5 milliliters in the scheme of this is roughly around here. Okay, the green dot, roughly. So, what if we add 10 milliliters? Okay, so 0.01 liters times a molarity of 0.1. So 0.001 moles of base were added. Recall that our moles of acid was 0.002. Sorry, I'm switching terminology. I think I wrote WA up here. The formula really was HB. Okay. So before we go further, can someone look at this and tell me what are going to be my moles for both of these? What will my, after 0.001 moles of OH minus reacts with 0.002 moles of HB, what will I get? Read.
You get 0.001 moles of HB and 0.001 moles of
Good. I need to add a page here. Hold on. So this has to make sense right now. This is really important to understand this. My original moles of weak acid was 0.002. That's how many moles of weak acid there were in the beaker when we started this whole process. By adding 0.001 moles of OH minus to this point, we have enough strong base to neutralize half of our original weak acid sample. If we neutralize half of it, that means the half that was neutralized has been converted into a conjugate base. And now I have equal moles of both parts. Okay? All right. So, what's our volume? Our volume is, we had 10 and 10, so it's 0.02 liters. So this is going to be 0.05, right? Yeah. Okay, so our ice table. So let me ask you something here. 0.05 plus x are the way what we simplified earlier, right? How we said they had to be about 4 orders apart. 4 orders apart is ultra conservative. Most textbooks say 3 orders apart. Some say 5%. Imagine for a second that let's consider ignoring the addition and subtraction of x. Wouldn't that mean this simplifies to this? Right? And of course, the 0.05 over 0.05, doesn't that itself drop out? So in this calculation, we're going to find that x is equal to 1.8 times 10 to the minus 4. X is equal to the Ka. Now, let's do this both ways. Let's prove it to ourselves and plug into the calculator without simplification, and then see what we get. Okay, so without simplification, I got x to be 1.7, we'll call it 1.79 times 10 to the minus 4. And with simplification, it's 1.8 times 10 to the minus 4. That's pretty close. All right? So, the negative log, the pH is just going to be the negative log of the Ka. So pH will be 3.748. And again, does this make sense? We added a little bit more base. Are we a little bit higher than where we were in the previous step? Yeah, we're still in the buffered region. We are at, this is called the half equivalence point. Okay, this is when 1/2 of the original acid is neutralized. 1/2 of it. This is not the equivalence point. Right? The equivalence point is different. We define the equivalence point differently. This is the half equivalence point. We have not neutralized all of it. We've only neutralized half of it. Okay, so this point on our graph is right here. Okay. Moving on. So that was 10 milliliters. Let me go back to this picture here and just explain something. Okay. So far we have calculated this. We have calculated this. And we have calculated this. What do you think is going to happen? And let's put some numbers on here. Right? So this was 10. This was 5, right? We did 5? Okay. What do you think is going to happen if we calculate the next problem with 15 milliliters? So far we did 0, 5, and 10. Between B and C. I would predict right here. Does that make sense, guys? Okay. All right, so we don't need to actually carry out that calculation because when we do, we're going to see that our pH is going to be slightly higher than this one, probably by the same ratio that this was higher than this one. All right, so let's calculate at 20 milliliters. I'm just going to fast forward a little bit. Let's do 20 milliliters. So 0.02 liters, 0.1 molar, 0.002 moles of OH minus are added. Remember that we started this with 0.002 moles of HB of the weak acid. How much will HB decrease by? How much of the weak acid will I neutralize? All of it. All of it. And I am making something, right? I'm making a conjugate. How many moles of the B minus conjugate will be made? 0.002. This is no longer a buffer. When this happens, we say buffer capacity has been exceeded. In other words, it's no longer a buffer. No buffer left. You only have the conjugate, and the conjugate is a weak base, and therefore you treat this problem as a weak base. So, if this is a weak base, that means your ice table equation looks different. It now becomes focused on the weak base, B minus. And so to solve this problem, you will need to recalculate what the concentration of B minus is. And to solve the equilibrium portion of this, you need a Kb value, which I did not give you. Where do you get such Kb value? Google it. Use Kw, right. Kw is equal to Ka times Kb. And so if we need Kb, it's Kw over Ka. So 1 times 10 to the minus 14th over 1.8 times 10 to the minus 4 is our Kb. Okay, so 5.56 times 10 to the minus 11. Everybody agree? You get that? Okay. So let's solve for what the pH is now at the equivalence point. Oh, how did I know I was at the equivalence point? What's the definition of the equivalence point? Yeah, the moles of acid and the moles of base are equal. If that happens, that means all of the original species is neutralized. 0.002 and 0.002. We are at the equivalence point. Okay, so let's recalculate our concentration. We've got 0.002 moles of base that we need to divide by what is our cumulative volume. We added 20 milliliters and we had 10 initially, so our total volume is 30. So we're dividing 0.002 by 0.03. So 0.0667 is our initial concentration for the base. We enter zeros for our products because this is just the start of the reaction of the basic ion. Nothing is there yet. So fill out the rest. We have our KB. Let's solve for what X, and of course, very important for you to recognize now that X is no longer equal to H+, because this is no longer an acid. Okay, I get X to be 1.93 times 10 to the minus 6th. Taking the negative log of that gives me the POH to be 5.715. So that means our pH will be 8.285, and that makes sense because once I neutralized my weak acid, I made a basic ion. So the equivalence point pH should not be neutral. It should be something higher than 7, and it is. How are we doing, guys? A little perspective. Let's go back to the picture, to the graph. All right, so this is where we are now. The equivalence point, the moles of the acid and moles of base are equal. That is what happens at the midpoint of your jump. Okay. Now, oddly, if I continue to add more base, remember, there's no longer a buffer. There's no longer anything left in this solution that can neutralize OH minus. So by adding any point here after point C, here, it's no buffer anymore, and there's not even equilibrium anymore. Okay? It's just based on the stoichiometric excess of your titrant. Watch. Okay, so let's calculate, what's a color I haven't used? Let's do 22 milliliters. All right, so 0.022 liters, 0.1 molar, 0.0022 moles of OH minus. Remember, again, and I'm still writing the original amount of weak base, so it's clearly shown how much of my products are made. Okay, so plus 0.002 moles of HB. The result is that there will be 0 moles of HB remaining. There will be 0.002 moles of B minus produced. And do you see that there will be 0.0002 moles of OH minus in excess? Right? 0.0022 minus 0.002. We added more base than we needed to neutralize the acid. So now we're dealing with excess base. All right. So because of that, let's calculate. All of your pH calculations are based on the excess. Because it doesn't matter that there is weak base produced. What produces OH minus better? OH minus itself or a weak base? OH minus itself. All the pH, it doesn't really matter if there's a weak base present. So we just really need to recalculate what the molarity is, 0.0002 divided by a volume. What's my volume now? 32 milliliters. Okay, so our molarity is 0.00625 molar OH minus. And negative log of that means the pOH is 2.204, which means the pH is 11.796. There is a way to prove that the weak base doesn't matter. I need to set up a nice table, and I plug in the molarity of the weak base, and I plug in the concentration of OH minus here, and then at the end of the day, the value of X that I would have to add to this is negligible, and the pH will be unchanged. Okay. So let's wrap this up. We just calculated 22 milliliters right here, right? 22 milliliters. How you calculate the pH on a titration curve depends on context. It depends on what is going on. There is no one simple method of calculation to calculate any point. You need to pivot, and you need to figure out what's going on and how you're going to start it. At the very beginning, there's no buffer. It's simply a weak acid, so it's simply Ka. Anywhere in this flattish region here, you need to reduce your original moles of your weak acid as it's neutralized, and it means you're creating conjugate base, which means this is a buffer. At point C, you have exactly neutralized the moles of your original acid. And therefore, it's not a buffer anymore. It's just a weak base problem now. And any point after C, it's just based on what the concentration of the titrant is. And then there's a special point here, halfway between A and C. We call that the half equivalence point. That is when your moles of a weak acid and conjugate base are equal to each other. And what that means is your pH is equal to the pKa. You know, actually, and I think maybe I didn't talk about that yet. So let's back up and talk about that. Okay. So here's what you know. You guys have written this so many times now. You know this. Except that I can't write it. Right? That's your law of mass action for any weak acid. Let's rearrange this and solve for H plus. Okay, so to solve for H plus, this becomes Ka times HB over B minus, and that's equal to H plus. Do you guys understand that? I'm just moving stuff around. Multiply both sides by HB, divide both sides by B minus. Okay? So what if I took the natural log of both sides of this? I'm sorry, not natural log, negative log. Let's say I took the negative log of both sides of this. All right? So what that would do is I would get the negative log Ka minus the log of HB over B minus equal to the negative log of H plus. All right. The negative log of H plus is otherwise known as what? pH. So the negative log of Ka is known as pKa. Now, rather than have pKa minus log of HB over B minus, let's flip the sign on that and invert what's in the ratio. And so pKa plus the log of B minus over HB is equal to pH. This is the formula that's used when you need to find the pH of a buffer quickly. It avoids ice tables. It's a lot less calculations. And here's why. I forgot my brackets here. Right? These brackets in here, what do brackets mean? Concentration, molarity, right? Aren't these two in the same beaker? So if that's the case, that means moles of B minus over volume X divided by moles of HB divided by volume X, the volume drops out. So really it's a ratio of moles then. Does that make sense? Okay, so because of that, you don't have to worry about calculations for volume or concentration. You just need the moles when you're using this. This formula has a name. This is called the Henderson-Hasselbalch equation. And whenever you need to find the pH of a buffer quickly, just figure out how many moles there are of the basic ion, figure out how many moles of the acidic ion are, take the log of the ratio and add it to the pKa, and that's your pH. There are some drawbacks though. And this is something you should be aware of. This equation works for most of the buffer, but there's times where it fails. So here's when you can and can't use it. Okay. So the buffered region we said was kind of like around here, right? The flattish portion, right? The Henderson equation works fine for that buffer region. But it is not accurate here or here. In other words, it does not work at the extremes of the buffer region. It doesn't work well at the very, very beginning of the buffer, and it doesn't work well at the very, very end of the buffer. And that's because of some assumptions that we were making when we write out our ice table. So it's one of those use at your own risk type things. It saves you a lot of time, but if you feel like they've barely neutralized anything, or if you feel like you're practically right at the equivalence point, you should not use this equation. You should only use it when you're close to the flat part. Okay? That's the only time it's going to be accurate. Now, having said that, on the AP exam, whenever there has been a buffer problem, I will say in the past 10 years, I have not seen a situation where you can't use this. In the past 10 years, this has always worked. All right? But I am just, you need to be aware, right? I don't know if that would be really mean for them to like start a buffer problem and then they give you like 0.2 milliliters into a problem. What are you supposed to do with 0.2 milliliters, right? You're just at the start of the buffer. You probably shouldn't use this. You probably should use an ice table. I will say this, an ice table will always work. An ice table will always work, wherever you are in the buffer. Because this is a shortcut, it makes some assumptions. It's meant for convenience, but there's times where it's not accurate. All right. That's enough prattling on about this. My guess is